Hello, good day, good afternoon, good evening. Welcome to our AI webinar. My name is Branko, and today we will be discussing a little bit more about why you really need data and AI in business, and of course AI in general. So let's just start. This is our agenda overall. These are some of the questions we will be discussing today, starting of course with the question what is AI, and maybe even more important, what is not. We'll be diving into intelligence a little bit, describing what are the closed systems. Of course, we'll get in touch with data, describe what are different shapes and forms in which data comes in. Then from there, we'll move on to specific subfields of AI. We'll talk a bit about organizational and, of course, business aspects of data. And at the very end, we'll, of course, mention some of the state-of-the-art achievements and technologies in AI today. From there, we'll also move on to a more practical part in which we will be talking about specific use cases we worked on in Quantox. So let's just start. Okay. So the main question is really what is AI? And as you can see on the screen, these are different definitions of AI provided by different actors in our life market. So if you take a look at, for example, what PwC says about AI, it says it's a set of technologies that can understand, learn, and then also act based on some information. Very practical definition, if you want. On the other hand, if we go and ask people from Stanford, they will be probably giving us something a little bit different, and they will mention science, engineering, intelligent computer programs, and how these programs can pretty much understand human technologies, which is quite different, I would say. At the very end, let's go to the US government. They say it's a system, it's a computerized systems that exhibits behavior, which is commonly thought as of requiring intelligence. These definitions are, we can absolutely say, all true and correct, also very broad, and also, I believe, very promising. In real life, it seems to me that all this works slightly different when we have to work with some constraints, if you want. So maybe we can actually move and talk a little bit more on practical level about what AI is and what it isn't. And we will start by providing these three statements. AI is a system that outperforms humans. It's not sentient and it's not general. From everything which we previously saw, these are all much different. Previously, we were talking about understanding, learning, acting. We mentioned intelligence several times. And now we are pretty much downscaling to something that's much more practical, if you want. So let's just explain these three. Okay, what does it mean that these AI systems are outperforming humans, right? We are giving here an example of AlphaZero, which was created by Google DeepMind, and it's a very powerful solution if you would like to play chess. In fact, if you decide to play chess with AlphaZero, there's absolutely no chance that you will win. AlphaZero is unbeatable if we are talking about chess. But what is really a chess? Well, chess is a closed system. And what is a closed system? Well, a closed system is a system which works based on, let's say, previously or defined in general rules or constraints. Without those rules or constraints, it would pretty much be an open field where everybody can do whatever it wants, but it's a game, so it has some rules. And if you would like to play chess with a fellow colleague, there's always a chance that you will get beaten or beat him. But if you play with AlphaZero, you're going to lose. On the other hand, if you ask it to, I don't know, tell you what is the capital city of France, or ask it to propose a business strategy, AlphaZero is going to miserably fail. Why? Because it really doesn't even know about business strategy, or what is France, or what is Paris, if you want. Second statement, it's not sentient. Well, look, doesn't feel, it doesn't understand, so it's kind of very limited in that way. And as we said, it's not general. General is something that we kind of already described when we said, okay, AlphaZero, it's very good at chess, doesn't know anything about France, doesn't know anything about business, doesn't know anything about strategies. Its knowledge pretty much exists only within a field of chess. And from there, we can start thinking more about, let's say, different levels of AI or different stages of AI. We pretty much think in 3 different stages. Super AI, in which machines are much, much smarter than humans. And, well, definitely we are not there. Will we be there someday in the future? I don't know, who knows. Then, slightly lower stage of AI, it's general AI, or something that is also known as artificial general intelligence. That one is pretty much about taking knowledge from one domain and transferring that knowledge to the other one. Again, as we previously said, there is no such a thing. AlphaZero, good at chess, very bad at business strategy. Not just bad, it doesn't know anything about it. At the very end, we come to something that we call narrow AI. And narrow AI is, let's say, type of AI, type of artificial intelligence system that is dedicated to assisting or taking over specific tasks that humans already perform. These systems are designed in a way that they, let's say, exist or work only within closed systems. And what is even more important, they need data to represent those systems. Okay, so far we were talking about AI, its definition, what it can, what it cannot do, how good it is. But let's really try to dive a little bit deeper into its basics and also, mention several business aspects. Since we already defined narrow AI and mentioned importance of data, I believe that it's absolutely important to start this talk by mentioning data. And if you are talking about narrow AI, if we are talking about narrow AI systems and solutions, it's the data that we give to it which dictates its perception and its scope. There are different types of data. We are here mentioning tabular and non-tabular, but you can also think about it as structured and non-structured. If you are talking about tabular or structured data, then as you already see and probably know, we are talking about rows and columns, Excel sheets if you want. But then, non-structured or non-tabular data, well, here we are giving examples of images and text, but we should also not forget about audio. And if we are talking about these different types of data, then we should also be talking about different systems it can represent, or these data can represent. And here's a list below, right? So we are talking about stock markets, but we are also talking about, let's say farms, city traffic, different language systems or different language domains, if you want, talking about business, talking about legal, medical. We are talking about, X-ray images or I don't know, even device malfunctioning data, IoT data, and so on and so on. And then there is a question, okay, but with all this data that we are now mentioning, what we can do about it? How can we take advantage of all the data that we are already collecting, or maybe we can collect in the future? What kind of AI, what kind of narrow AI, to be precise, we can create? Well, again, just put yourself, or let us put ourselves in shoes of, I don't know, somebody working in, let's say, manufacturing, or maybe healthcare, or maybe I don't know, legal. And let's try to imagine what kind of solutions based on AI we can build. If you're talking about legal and NLP, then think about, like, I don't know, understanding context of legal documents, or let's move on to stock markets and just, I don't know, try to predict stock prices in the future, or, I don't know, diagnose some rare diseases. These are all possibilities, different possibilities you can think about if we are talking about narrow AI solutions. But then the question is, okay, how that's, if you want, magic actually happens, right? So let's just try to answer that one quickly. When we are talking about artificial intelligence, we are pretty much talking about different subfields. And here in this scheme, you can see us mentioning machine learning, natural language processing, computer vision, right? These are all, if we go back to one slide, kind of match these types of data very well, right? So there are different approaches or techniques, if you want, that we can use to build these narrow AI solutions. Computer vision obviously works very well if you are working with videos or images. Language processing kind of covers speech and text. And then machine learning, or how we like to call it, traditional machine learning, is pretty much all about tabular data. But let's also mention another way of looking at, let's say, AI or machine learning. Here we have a definition of 3 different subfields of learning: supervised learning, unsupervised learning, and reinforcement learning. And they do cover different types of data, but in a slightly different way. So supervised learning, as it's written here, is learning from already labeled data. What does that mean? Well, literally it just means the data that we actually collected was checked by some people, and then those people were able to put some, let's say, labels, or let's say classes to it, right? That kind of describe it a little bit better. And then you also have unsupervised learning, which is, well, same data, but just with, humans not intervening and not putting any additional work there. And then there is also reinforcement learning. But what are these different types of learning, right? So supervised learning, at the very end, really think about it as our systems being able to predict something. Predict how? Well, based on those labels or values that we attach to it. And here we are mentioning one example of supervised learning: spam detector. We have a bunch of emails, and then what we do with it, we kind of classify it into 2 big groups, spam, not spam. And then we take advantage of machine learning to build ML systems or AI systems that will be able to detect what is spam and what is not. Unsupervised learning, well, that one is, as we already mentioned before, just, let's say, clustering based on context. You have a bunch of documents or a bunch of data points, bunch of customers in your retail business, for example, and you would like to understand underlying patterns that can help you, see or identify different groups within that data. And then at the very end, reinforcement learning based on feedback or learning based on reward. We already mentioned one example of that type of AI, and that is AlphaZero. AlphaZero is very powerful reinforcement learning based system that knows how to play chess. It learned how to play chess just by watching, if you want, a bunch of games which were played by humans. Okay, so let's move on from this more technical aspect into more business or organizational aspect of AI. We mentioned lots of different types of AI or machine learning, and we introduced many different terms and definitions. We mentioned a couple of different projects or possibilities on what kind of AI systems you can build. But at the very end, this is all about, well, making some success using AI. How that can happen. How we see it? We see it as an overlap of three different topics or three different things. First, domain expertise. Second one, data. And the third one, right, AI technology. Okay, but what does that really mean? Well, at the very beginning, I believe, or we believe, that it all starts with data. And there is even a saying in data science and AI which says garbage in, garbage out. What does that mean? Well, it means that if you have bad data, if you have data which is not of good quality, you are definitely or most surely not going to be able to build any kind of success based on that. So data really has to be of good quality. And it's a different topic, but there are many different things you can do to make sure that you have good data. After all, what is also very important is that, look, based on what kind of data you have, you're also going to be limited in terms of solutions or AI systems that you can build on top of it. Then there is domain expertise. In AI, machine learning, data science, if you want, these are all very, very similar terms. You have a bunch of technical people working on. And in many cases, the fact is, we as data scientists or we as machine learning engineers don't have that deep knowledge of the domain or, let's say, industry in which your business operates. So we need help, and we need help of, let's say, manufacturing operators, marketing experts, financial experts, or any kind of people that work closely within one domain or within one business. Their knowledge can help a lot in building successful AI solutions. At the very end, it is about choosing right technology, and in many cases, you should or we should start by building very simple solutions, and then based on first success that we see, then we can start building something that's going to be more advanced and help us even further. And now let's just quickly mention some of the state-of-the-art solutions that nowadays exist. Here we are mentioning three of them, and there's something which is that was recently published by Google, which is called Lambda, and then here in the middle you can see Tesla logo, and on the right side there is something that is titled as Stable Diffusion and also DALI 2. These are all very advanced systems. For example, Lambda, well, at least Google does claim that this is a very powerful NLP system that can pretty much answer all kinds of questions based on just based on some input that you provide. Some Google engineers went that far even to say that it's sentient. In the middle, Tesla, we all know about that company, and it's very known because of its autopilot solution, which kind of enables us to just sit in the car and allow its systems and software to drive us without any intervention. And on the right side, there is something that's called Stable Diffusion, which is able to create some really interesting art just based on textual input. These are all well advanced, but on the other hand, also I would say, probably something that we are not going to see in our businesses very soon, right? And believe it or not, all of these solutions come with its own limitations. They all have their ways to fail. They are not perfect. And, we should be looking into future, with a positive way, and try to imagine how someday our businesses will or can look like. But at the very end, we also have to be with both feet on our ground and think about solutions that can help our businesses in everyday life and business. With this, I'm going to conclude and finish my part of the presentation. I would like to thank you all. Now, I will be joined by my colleague Nicola, who will be telling you more about some use cases and AI solutions. We will be able to, let's say, maybe bring you closer to what we do and show you how we were able to help our clients and partners. Thank you very much.
Hello, everybody, and thank you for joining us in this webinar. My name is Nicola. I'm a senior data scientist here at Quantox Technology, and throughout the rest of this webinar, I'm going to talk about some of the AI use cases that we've been working on in our company, and generally talk about how we utilize AI, how we think about it, and how we go about AI projects in general. So, without further ado, let's dive straight into it. So, case number one, we are going to talk about e-commerce. So, this is a project that we did for the client of ours that had a online furniture store. So basically, the idea was to sell furniture online, simple as that. They had their website or web shop, if you will, and they could have their users search for the products they need, and they could filter that search, more importantly, based on their preferences. So basically, you can filter through. You can filter based on product types. So, for example, if you want a couch, or if you want a dining table with a set of chairs, or if you want whatever, you can filter through that. But also, you can filter based on color, based on material, based on product type. I already mentioned product type, based on manufacturer, and so on. So, how is it done? So, how is this information initially being provided to their web shop? Well, just like Branko mentioned in the first part of the webinar, we have something called manual labeling. So our client had a system of manual labeling, basically. So they were essentially paying people to take ads and label them, right? So they were prompted to type in the product type, to type in the color, to type in whatever is needed for the search filtering, and that was the way of gathering this information. So you would agree that this task is rather simple for humans, but can be actually dauntingly difficult for a computer. So let's see how we go about this and how we are transferring this business problem into essentially a data and AI problem, if you will. So the first thing we do is we ask ourselves, what do humans do exactly when they go about this? And we are going to try and answer this question algorithmically, so to speak. And maybe this is sound confusing, but bear with me. So what would a human do? Well, human would take an ad and like see or read what's in the ad. So the next question is, what does the ad consist of? Well, on one side, it consists of the image. So you have the image of the product that's being sold. For example, as you can see on the leftmost picture, that you have this like black table. I think it's a table, I don't know. But yeah, you can see it, and you as a human, you just know it's a black table, right? So you're prompted to write the product type somewhere. So you type down table, and you're prompted to write color somewhere. So you type down black. And now, if you want to make AI do this, what you want to do actually is create a system that emulates kind of what the human would do in this situation. And so, like Branko mentioned in the first part, we need data to work with. So what is the data that we used for solving this problem? Well, it was the data that was manually labeled by humans, unsurprisingly. So there was a lot of ads that already were running on the website. So we took a sample of those ads. So we took images, we took text, and we took the labels provided by humans, and then we made AI learn from it. So in AI terms, what we have here is a combination of computer vision problem and natural language processing problem, because on one hand, we have these images that we need to analyze and something maybe written in text. So we kind of need the system that can handle both and then combine the outputs to actually provide the information that's needed, which is basically the product, the color, material, etc., everything that I mentioned earlier. So now that we have this situation clear, so now we know what we need to do, let's kind of show you how we thought about it from, say, software perspective or development perspective, if you will. So here you can see a diagram that kind of represents the process that we're going through when working with these type of tasks. So on the left-hand side of the diagram, you see that there is a part of the process that says sample manually labeled data, which is what I just described on the previous slide. And down below, you see that we hold out a fraction of data aside. Why do we do that? Well, the reason is simple. Once we train our models to actually output the information that we desire, we want to actually test them on the data that they never seen before. So in our lingo, it's something called train test split, if you will. So train is the section of the data that you use for training the models, and the test the section of the data that you use to evaluate your models on before actually selling it to anybody. So in the middle of the diagram, then you proceed towards training. So this is a very simplified diagram. There's a lot of steps that actually happen, in between sampling the data and actually training the models, such as data pre-processing stuff, but I'm not going to bother you with that. So what we do essentially, we train some machine learning models to perform the task that we give it to them. So we have two types of machine learning models that we're dealing with here, and that is the direct consequence of two types of data that came in. So we have a vision model, a computer vision model, that we're training to detect objects, which is a known task in computer vision, which is object detection. But we're training specifically to detect the furniture that's visible in these pictures. If you go one slide back, you can see these images of furniture. So if there's a lamp, we want to train a model that says, okay, this is a lamp, definitely. Then on the other hand, we have text, which describes the product that's being sold and probably holds information about why not even color, but also manufacturing material, stuff like that. So we want to train a language model to understand text and separate for us what's the information of interest in that text and what's basically garbage, what's irrelevant for us. Then when we train those models, we combine their outputs in a way that the desired information is obtained. And at this point, we say that we have some training model. We evaluated on the data that we left aside Remember, I said we're always leaving a fraction of data aside, usually about 10 to 20% of data. And when we're happy with the results, we can proceed with what we call deployment. So basically, that is a stage when you have a model which performs your task in a certain degree of accuracy that's satisfactory for the business. So you can deploy it. What deploying means is basically creating some sort of a web service, let's say an API maybe, which can return the desired information. So that's exactly what we did. We built like some sort of an API on top of our model, so our clients' developers can integrate our model in their website, in the web shop, essentially. So yeah, and for those of you who might be interested in a little bit more technical detail, what we use specifically for this task is a combination of two known models, one coming from the realm of computer vision and the other coming from natural language processing. The computer vision model would be YOLO for object detection model, which stands for you only look once, which is an architecture that can be trained on any custom data. And for text, we use universal sentence encoder, which basically is tasked to extract valuable information from text. These are basically two large neural networks pre-trained to a certain degree, and so on. As for results, our model, the combination of our models essentially was accurate at about 70% of the time. And we also provided something called the confidence interval, which kind of gives us the upper and lower bound of our accuracy, allowing for a certain degree of errors. For example, 5% in our case. So what we say is 95 times out of 100, our accuracy is going to be between the upper bounds and between the lower bound and the upper bound. Average is about 70. And you might think at this point, well, it's not really an impressive number. I mean, it's not much higher than a chance. But the thing is, when you're working with data labeled by humans, sometimes you have to allow for these lower numbers because of the simple reasons, such as once they did the labeling, for example, could label stuff differently, but they're essentially the same stuff. For example, if you look at the image and there's a couch that's being sold, for example, one labeler could type in the word couch, while the other labeler can type in the word sofa, and they actually think about the same thing. Or better example with colors. If you have something that is kind of bluish or something, one could type this is like blue color, and the other can type this is light blue. And then you have to find a system that can actually, compare these labels and evaluate. So to which extent do you allow, these different labels to actually be the same labels? So kind of those are the tricky parts after even training the model. So we have to, find a way to actually evaluate the model and then go to our clients and say, this is the number. It's really tough number to compute, actually. And based on what we've seen on this project, this number is realistically above 70%, but due to these, obvious limitations that we had with the human labels, we came up with the number of like 70%. And with this, I would like to conclude the e-commerce case. And now I would like to show you something a little bit different. And that something would be anomaly detection. More specifically, anomaly detection in cybersecurity. Well, let's first cover the basics. So what do we mean by anomaly detection? By anomaly detection, we mean, well, it's pretty self-explanatory. It's any kind of behavior that deviates from some sort of a expected pattern, some sort of normal pattern. So in the first part, Branko mentioned emails, spams. So that's a great example of anomaly detection. So whatever mailing service that you're using probably has this feature called spam detection, and basically they're automatically analyzing emails that come to your inbox and automatically determining if they're spam or not, and then they put those for you in the spam folder. And in cybersecurity, on the other hand, which is the main part of this anomaly detection part of the talk, we can apply the same idea to identify if a network of computers is being attacked by hackers. So let's see how exactly are we dealing with this issue. Describe a little bit what are we looking for exactly when we say we want to detect hackers attacks. So on the right-hand side, you see probably the world's simplest client-server architecture diagram. But essentially, this is what it's all about. So there's one central server that serves one or multiple clients, and each client sends a certain request to the server, and then the server's job is to send some sort of response back, right? Simple as that. So in the request, there's some data the client sends. For example, the server needs to authenticate that client, and then says, okay, you are either eligible or non-eligible for a response, and consequently send a response or don't send anything. So there could be a lot of types of different requests that could be very simple, going anywhere from, hey, give me a weather forecast for October, or give me a profit and loss sheet for the company for the last 3 months. Or it can be, give me a profit and loss sheet and also go and delete the entire database. So that would be a hacker's attack, and they tend to come in disguise. So what I just described was essentially a type of attack called an SQL injection, which is really, old way of attacking a system. And today's systems have a really good defense from that. So nowadays it's not possible to perform this SQL injection, but you get the idea. So there's some kind of malicious intent within those requests that make our system vulnerable. So what do we do about this? So we are trying to make an algorithm that will predict that the hacker's attack is going to happen before it's too late, and it's usually too late, once you realize you're being hacked. So how do we feed this system data? So we mentioned that the data is really important. So what data does this system learn from? We're collecting historic data from some sort of computer networks from the times that we know a hacker's attack happened. And then we make the AI system learn from it. So we have history, and we're making some sort of a software that can actually detect hackers' attacks in the future, just based on historic data. And in our specific example, we were talking about 120,000 examples of historical attacks. So that was our data set. Speaking of data set, moving on. So the data that we were dealing with was tabular in this case, unlike the previous case, which was unstructured, not tabular data, images, text. In this case, it's tabular. And what we're doing here is we're trying to classify each record in this table as, does it belong in one of these five categories? So we have 4 categories for different types of hackers attacks and 1 category for a normal state of network. So when you look at this table, well, standard table, rows and columns, right? So each record, each row in this table represents a state of a given network at one period of time in history. Each column is some sort of a network parameter. For example, the duration of the connection, the bytes transferred, during the request-response cycle, and so on. A lot of different technical stuff that I wouldn't really go into details here. But essentially, we want our AI to take this tabular data as is and learn how to classify the network based on these parameters, these what we call features or columns in terms of tables, to predict to what group does that record belong to. Is it normal? Is it DOS, probe, U2R, R2L? Now I mentioned some of the types of hacking attacks that can happen, so let's go really quickly over them. So you have the DOS, which is a denial of service type of attack, which essentially happens when you're actually trying to exhaust the server, so you can't really return any kind of response. And what's interesting about it, it can happen without even a malicious intent in the first place. For example, if it's a Black Friday and everybody's shopping at that time, they can crash the server, right? I mean, but we are interested in the ones that are actually malicious here. Then we have probe or port scanning, which is a really hard concept to grasp, but essentially what it does is trying to access like wires and hardware stuff within the system and try to extract confidential information from that. If there's any cybersecurity experts in the crowd, please let me know if I got this definition correctly. And then there's user to root and root to local, which are pretty similar, but they're using different techniques to actually gain root privileges or admin privileges for non-privileged users. And okay, so now that we understand the data, let's move on and see what kind of AI is appropriate on top of this and what kind of system can learn from this data. So we have a classification problem in AI terms. So what does that mean? We are classifying each data point, each segment, or each row in the above-mentioned table into predefined classes or groups, which are our types of hacking attacks. For example, if you look at the diagram on the left, you can think of class A as DOS, you can think of class B as probe, for example. We have 5 classes, but we're just illustrating the point with this diagram. And more specifically, again, for those who are a little bit more interested into maths and details of this, the specific algorithm that we use for this is support vector machine. So this is the classification algorithm that was developed by a Russian scientist by the name of Vladimir Vatnik. It was about 50 years ago when it was first proposed. Anyways, there's a plethora of these classification algorithms, but we opted for this one to try and solve the hacking attacks problem. And now we can look at the results of applying support vector machine algorithm to this data that I described earlier. So, okay, don't be confused with these visuals. I'm going to explain them. So on the right side, you have the statistic accuracy test that says 81%. So you remember that we always hold a fraction of data aside for testing our model. And on that fraction, we are 81% correct when classifying the states of network and types of hacking attacks. So what you see below is this matrix that we call confusion matrix, which is because it's really confusing. And I can show you how to read it. For example, let's look at the DOS row and column. And you have this true label and predicted label. So label is essentially a type of a hacking attack. You can call it label, you can call it target, you can call it class, category, whatever. We use these terms interchangeably. But the way you read this is, okay, in all of examples of the DOS denial of service attacks in our test data, the one we put aside, our model, the support vector machine that we trained, got it right, classified it as denial of service 5,696 times. So that's the number in green. It confused it with the normal state of network 7 times. It confused it with probe 38 times, and it never confused it with the other 2 types of attacks. And you can read the rest of the matrix in the same fashion. So what we really care about here is making our model robust in terms of optimizing for a small number of, let's say, false negatives. I know I'm introducing a lot of terms here, but just bear with me. What false negative is when there's actually attack happening in the network, and our model says it's just a normal state. So that is dangerous. While if it confuses the types of attacks, it's truly a DOS, but it's got it as a probe. That's not really a problem. It's still going to alarm somebody in the company to actually take a look at it and actually react appropriately to it. So why do you need this in your business? Well, if you have a large network, you will have to employ a lot of system administrators who constantly have to watch 50 parameters. And that's just in this case, as probably hundreds or thousands of parameters in the network, and watch them in real time and always take care if the hacking attack is going to happen or not. While you can also build it the AI model which does it for you, so you can set up like something like automatic alarms when it thinks there might be a slight probability that the attack is actually happening. So this would conclude the anomaly detection / cybersecurity case that we covered. And I would like to summarize everything that we talked about tonight and bring some conclusions to the table. So what we've seen so far in this webinar. So there is no general AI, and there's a good chance that we will not see this in the foreseeable future. Also, almost all AI tasks could be divided into supervised, unsupervised, and reinforcement learning, and we actually aimed to kind of bring this notions closer to you in a way that, for example, if you own a business, that you can recognize and say, aha, this would be a good candidate for an AI test or something like that, without even having a technical background whatsoever. So just to be aware of what can be done, and if you recognize if it's a supervised, unsupervised test, even better, right? And also, what we saw tonight is that these teams that we work in are often multidisciplinary and require a blend of engineers and domain experts, and really the success is going to depend on having all of this stuff in place and taken care of properly in organizational aspects and technical aspects and all other stuff. And about the use case, we covered e-commerce and cybersecurity, but essentially all these algorithms, all this fancy mathematical stuff like support vector machines, object detection algorithms, everything can be and is currently being applied to a much larger set of industries, such as ones you see in this slide, for example, agriculture, financial, biology, medicine, you name it. So yeah, I think this concludes our presentation. I hope we explained some of these stuff. And now we will take some questions. Please feel free to ask questions. We will look at the chat and try to answer as much question as possible. Thank you. Okay, I got one. Is there any specific reason why support vector machine is used for cybersecurity attack detection? Okay, yeah, good question. So the answer is yes and no, but whenever you are dealing with some sort of a classification problem, at least how we do it, is you are trying to build a baseline model. And for that, you can go for, you have like a bunch of classification algorithms at play. You just pick one. You just pick one and make a baseline model. And based on the results of the baseline model, that tells you, okay, was this a good choice of a model, for one? For two, it tells you what you can do in terms of data preprocessing, data cleaning to improve your model, and a bunch of other things. So it's a really iterative process. And in our particular case, support vector machine in the baseline showed 81% of the accuracy, so we'd probably go with that. I think, yeah, I hope that answers the question. I got another one. Is the supervised learning strictly tied with the text type, or is it applicable on other types of files as well? No, it's absolutely not tied to text only. We just gave one example that covers textual data. You can, for example, here's another example. So let's say you have a retail business and you have a bunch of customers and you collect a lot of data about your customers. So for example, from what industry they come in, how often do they pay, did they get any discounts, blah, blah, everything, size of the company, the client company. You can cluster those customers and see what are the characteristics of each cluster, so you can have different business strategies towards each cluster of your customers, for example. I'm looking, is there any other questions? I'm scrolling through the chat. We can see AI is much better in predicting denial of service than any other sort of attack. Is reason for that network parameters or other attacks, or is it AI limits problem? Well, it's definitely not AI limits problem. What could be the case is that the denial of service was the most frequent case that occurred in the data set, which is something that we call class imbalance, and which is something that we optimize on. We just unfortunately didn't have time to cover and tonight's webinar, but yes, the keyword here is probably class imbalance. So DOS was much more present and in our data set that we work with. We keep in mind it's a baseline. There's always improvements that you can push for this. Okay. Yeah, I'll wait a couple of minutes to see if I get any additional questions. But yeah. Yeah, seems to me like there is no more questions. Okay, thank you for your attendance, and we hope that we clarified some of the stuff we are working on daily basis, and hope this whole idea of AI is much closer to you. If you have any additional questions, you can always reach out to me at Branko. These are our emails. Thank you once again for your attendance.